the first four terms and the Maclaurin series, okay? So if I wrote the first four terms here, let me think. Basically, I just need to get my thing to look like this. So I'm going to start with the basis, which is cosine x. Do you guys see that's the base, expression in this model here, in this function that I have. Okay, so what is cosine x? It says Maclaurin series, so that's center of 0. I do know the Maclaurin series for cosine x. Do you? Okay, it's an even function, so it starts with all exponents are even, so that's x to the 0. But x to the 0 is really what? 1. Okay, so I know 1 is an odd number, but x to the 0 is an even exponent. And so here what we're going to do is we're going to just put all of our even functions in. Now cosine does alternate, so make sure you alternate the terms. Okay, and I'm just going to go to 4 terms. I could do more to impress you, but I'm actually not so interested in doing that. Okay, and so then we're going to need our general term. Okay, you also have to memorize a general term. Since this is alternating, do you remember what the alternating factor looks like? Okay, then do you remember what the exponent will be since these are all evens? 2n, nice. And then what about the denominator? 2n, it looks exactly like the numerator. Don't forget to put plus dot dot dot, okay, because you put an equal sign. All right, and then what we're going to do is we're going to shift, we're going to change all the x's to x squares. Okay, you can do this if the center and the function shift together. So you can see I'm moving from x to x squared on the function, and on the center I have a Maclaurin series, and I'm moving to another Maclaurin series. All right, so the shift here is 0 and the shift here is 0, so I'm good with substitution. You guys good with that? All right, make sure you understand, guys, changing x to x squared does not mean squaring every term. Okay, what it means is replacing the x with an x squared. Okay, so make sure you understand that. And sometimes it turns out it's the same thing mathematically, but still make sure you're doing it right, because sometimes it's not the same. Okay, so I'm changing every x to an x squared. Every x is changing to an x squared. The quantity is changing. So this becomes, okay, this becomes cosine of x squared is equal to 1 minus x to the 4 over 2 factorial plus x to the 8 over 4 factorial minus x to the, I can't read my handwriting, is that 12, 6 factorial plus dot, 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 plus. Okay, let's think about the general term. Did I do anything to the signs? No. Okay, so I'm just going to copy that factor for changing signs. Okay, in here, what did I do to each of these exponents? Multiplied by 2. So do you see this would now be x to the 4n, because 2n times 2 is 4n. Okay, on the bottom, did I change anything to the denominator? No, so I'm going to keep that 2n factorial. Don't forget your plus dot, dot, dot. Okay, then what you do is now I need to multiply by x. But I have a question, guys. If I multiply by x on this side, do I just multiply, do I just tack on the x? Or do I multiply by the whole thing? The whole thing. Okay, so when you multiply by the whole thing. When you add or subtract, you can just tack it on. Okay. All right, so this is going to be x cosine x squared will be equal to x minus x to the 5th over 2 factorial plus x to the 9 over 4 factorial minus x to the 13 over 6 factorial plus dot, dot, dot plus. All right. Right here, guys, did I do anything to the alternating signs? No. Okay, so keep that factor right there, -1 to the n. All right, what did I do to each exponent? Added 1. Okay, so what's this 4n going to turn to? 4n plus 1. So this is x 4n plus 1. Did I do anything to the denominator? No. So this stays 2n factorial plus dot, dot, dot. Are you guys with me so far? Okay, and then lastly, I'm going to add the integral sign, the integral from 0 to 1. Okay, just for talking's sake, if this had not had limits, when you took the integral, you would put a plus c. Do you remember that? Okay, you need a plus c if it didn't have limits. But it does have limits. So what am I going to do at the end of this Taylor series? Do a win bar. Everybody good with that? So win bar if you have limits, a plus c if you don't have limits. All right. So you would take the integral of both sides. I don't think we actually have to take the integral of the left side. But I guess we could, if I said u is equal to x squared, then the derivative of that, the integral of that would be sine x squared divided by 2x. I think if I did it right, that is the integral from 0 to 1. And so this would be 1/2 sine of 1 is equal to. So this whole thing that I'm about to do is equal to 1/2 sine of 1, which is kind of cool if you think about it. Like just being able to estimate this with a polynomial, because who in the world knows what sine of 1 is? Okay, we don't know what sine of 1 is. You'd have to use a calculator to figure that out. But I can estimate it by just putting in, or taking the antiderivative and putting ones in. And let's go ahead and do that then. So on the right side, I'm going to take the antiderivative of each term. So this becomes x squared over 2. This becomes x6 over 6. This becomes x10 over 10. This becomes x14 over 14, plus dot, 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 plus. Okay, the general term's getting a little bit more tough. Did I change the alternating signs? Did I change the signs any? No. Okay, so I'm going to keep that. All right. What happened to each of these exponents? Add 1. Okay, what's 4n plus 1 plus 1? All right. Then how do I express this 6 and this 10 and this 14? Yeah, it's the same number as this up here, right? This is 4n plus 2. So I'm just going to copy that number down here. And then, do you see I didn't change this 2 in factorial, so I can just keep the 2 in factorial plus dot, dot, dot. Okay? But don't forget, I also need a win bar, right? From 0 to 1 here. And what that means is, first you plug in the 1. Oops, this is a 1. Then you plug in a 0. Then you slap a minus sign in between. Okay, make sure you guys understand. I'm plugging in the 1 into the x, not the n. You guys good with that? So sometimes students get confused between the n and the x. I do too. Okay, so make sure here, this is basically a dx problem if you think about it. We're taking the integral with respect to dx on both sides. So I'm plugging in the 1 as an x. So this is going to be negative 1 to the n. This x is 1. But do you see I don't really need to put it, right? Because 1 raised to any power, I mean, you could do it. But you guys see 1 raised to any power is going to be 1, right? So that's why I'm not going to put this expression here. But you could put 1 raised to the 4n plus 2. It wouldn't be wrong. It would just be a little awkward. Okay, then you copy the bottom. Okay, so first you put in the 1. Then you put in the 0. But do you see if I put in the 0, I'll get 0 minus 0 plus 0 minus 0 plus 0. Okay, I mean, you could do it. You could do it for fun. Okay, and then you slap a minus sign between. But do you see this term just wipes out? Or all these terms wipe out. Okay, so there is my answer right there. Okay. We're done with this problem, what they asked for. I got 4 non-zero terms, 4 terms, and a general term. Do you see that this is an alternating series? Do you see that? And there's this thing we learned, and they're not asking this question, but I'm just going to point this out. There's this thing we learned that if you have an alternating series and the terms alternate and the terms have a limit of 0, all these things have to be true, and the terms decrease in magnitude. Do you remember there's a special thing we could do to find the error? Do you remember find the bound of the error? And I would say, hey, you know what? If I tried to evaluate this, like I don't know what it is, but if I tried to evaluate this and let me just only take 3 terms. If I took 3 terms and I said, this was the approximation of f of x, and this would be f of x right here. If I tried to approximate that, the most that I'll be wrong by, because this is an alternating series that has a limit that converges, all these things are true, is if I draw a line here, the most that I'll be wrong at, meaning my error, okay, is bounded by this number here. Do you remember that? So my error is no more than the absolute value of this, which is 1 over 14 times 6 factorial. Okay, that's the most I'll be wrong by if I say this is my, this is the equal to my function. Do you remember that? Okay, yeah, Jonathan, you have a question? Oh, you're good. It's whatever I start approximating by. No, so like if I said my approximation was this, if I said this is my approximation, then that means I'm drawing a bar here, and it would be the 3rd term. Does it make sense? Yeah, I just made it up. Sorry, I just made up this problem. Okay, so I'm just saying now I'm saying my approximation is this. Okay, all right. So what we're going to do today is we're going to do the Lagrange error bound. Okay, and the Lagrange error bound works when you don't have an alternating series that converges. Does that make sense? Because this only works if you have an alternating series that converges, and not everything you have is an alternating series. Okay, so the Lagrange error bound says that for every Taylor series that you have, okay, if you draw a line here, your error is very similar to this last thing. So let me write this in notation form, see if this makes sense. This number here, isn't that really f of, this is a fourth derivative, right? Oh, actually, I don't know if it was a fourth derivative. Is it? Oh, yeah, it is. No, this isn't the fourth derivative, sorry. This is the n plus 1 derivative. So this is x squared, x6, x10, x14. This was the x14th derivative, right? Because this matched with this number right here, because this is a Taylor series. So this was matched with this one. So forget it. I'm not going to get you confused. But anyway, it has to do with this next term, the Lagrange. Okay, so let me keep on moving, and I don't want to confuse you, and we'll do a problem. Okay, so you have some definitions in your notes. I think you know most of these definitions. If you don't, you could read through them and make sure you understand the definitions, okay? But what the Lagrange theory says, that if you have a Taylor series, okay, and this is what the Taylor series is. I mean, this is the form for the Taylor series that you've memorized, okay? If you're trying to find the error bound, and the error bound, and it's not an alternating series, okay, and it's not an alternating series, then what you can do is say that your error, okay, is less than or equal to this bound. And this bound is this formula right here, okay, which is almost the same as what you had before, okay? It was almost the same. So what you do is you go to the next term that you have. So whatever your next term is, and you know, before your next term was this. On the alternating series, it was your next, your n plus 1 term. It was your next term. Okay, so you go to your next term. Okay, but instead of using this for your derivative here, instead of using this, okay, use a different derivative. And that derivative is the maximum that your derivative could be if instead of plugging in C, you plug in Z. Okay, and it's going to be the absolute value of that. And I just want to say this is super confusing because what the heck is Z, okay? And really, what the heck is all of this? But this is just like your alternating series. It just means go to your next term, okay? Go to your next term. But not only do you go to your next term now, this number changes when you evaluate your error is. And what this is the maximum that your next derivative could be at Z. And Z represents some number between X and C, okay? And what is C? C is your center, so that's super easy. What is X? X is what you're trying to plug in to evaluate. So, you know, at the very end, they'll say, oh, you know, plug in 2.3. What is your value now at 2.3? X is whatever they said to plug in, okay? And so if you're between your center and C, that's what your Z is. But I want to tell you, we're talking about Z, but you never have to find Z, okay? So I want you to say that with me, okay? I do not need to solve for Z. Can you say that? I do not need to solve for Z. Say it again. I do not need to solve for Z. Because since look at this formula, like, what is Z? Don't worry about it. Don't worry about what Z is. Z is some number between your center and your X value. And I'll show you what that is in a second. Some number. You don't need to know what that number is. But all you need to know is what that derivative is, what the maximum derivative is, okay, for Z. So let me show you what a problem looks like. Let's look at this example. Okay, this example here, they say, write the third degree polynomial for f about x equals 2. Okay, so what we're going to do is we're going to write f of x, and we're going to approximate that. Okay, we're going to write the third degree polynomial for f about x equals 2. Actually, I'm going to pause here. You guys do it. You've done enough homework that you should be able to write the third degree polynomial given this information here. See if you can do it. The center is 2. Okay, did everybody get the same thing I got? Okay, I put approximately equal to, so I don't have to put a plus dot dot dot. Okay. Now, do you guys notice that this is not an alternating series? Do you notice that? Because you have plus plus, right? That's not an alternating series. Okay. What else do we notice? Actually, we don't even know if it's alternating series that converges because we don't even know the function. So even if it were alternating series, we don't know if it converges or not. So, so therefore, we can't use the alternating series remainder bound. Okay, and then it says use this number here to approximate 2.3. Do you understand that 2.3 is your x, right? They're saying you've got a Taylor series. Your center, do you see your center is 2? Your x is 2.3, and they're saying give me what f of x is. So what they're saying here is they're saying plug in, everywhere you see an x, plug in 2.3. Okay, and estimate what this number is. So I'm going to go to my calculator. Okay, I'm going to estimate what this number is. So this is going to be 6 times, if I wrote all this right, 4 times 0.3, 6 times, no, 6 plus, sorry, 6 plus. Okay, 4 times 0.3, okay, minus, that's 3.5 times 0.3 squared, okay, plus 8 divided by 6. This may not be the best way to do this. 8, I'll do 8 times 0.3 raised to the third divided by 6. Actually, I don't know if order operation I was allowed to do that or not on the calculator, and I'll just hit enter. Okay, you guys can check me on this. Did you get 6.921? Okay, good. So 6.921 is what this function is if I plug in 2.3. Does everybody see how what represents my x? Okay, because later on you kind of get confused. X is what they're saying to plug in. Does everybody see how to get the center? If I said z is a number between x and c, do you see z is a number between 2 and 2.3? Do you guys see that? And actually z can be 2.3 too. And so it says use the fourth derivative that satisfies this inequality. No, this is the fourth derivative. The fourth derivative, you know, is less than or equal to 9. So this is the maximum fourth derivative. Do you guys see that? That's the most that the fourth derivative can be. And it says inside this closed interval. Okay, so guys, do you see that? Remember we said that z was between the center and x. Do you see that? So they're just saying for a number between c and x, this is the maximum the derivative can be. Use this information to find the error bound in this approximation. So actually all they're saying, guys, is, okay, use the Lagrange remainder theorem, okay? And what the Lagrange remainder theorem says is that if you approximate a number and you go to the, you go to the third derivative, okay, you are wrong no more than this number. And the next number is the maximum of your fourth derivative, because this was the third derivative, right? Or this was n equals 3. Okay, so this was n equals 3. This is n equals 2. Let's do n equals 4. So you do the maximum derivative at z, the absolute value of that. This should be x minus c to the fourth, right? This represents the next term, and you see the next term was x minus c to the fourth. Okay, so the center here was actually 2. The x here, guys, what should I plug in for the x? 2.3. Okay, so then what you do, and this number here is actually 9. So you go into your calculator and you just put this in. This is really 9 times 0.3 raised to the 4 over 4 factorial. That's my error bound. That's the most my error will be if I use an approximation of 6.921. So this is going to be 0.3 raised to the 4th power times 9 divided by 4 factorial, which I think is 24. 4 times 3 times 2. So this is 0.0030375. Okay, that's the most my error can be. Actually, they should tell you how many decimals to go. If they don't, you only have to go 3. Okay, but I'm going more just because it's an error, and I know I'm about to use this number. Okay, then it says, use your answers to find the interval Okay, so what you're saying is, since the most your error can be is this, then what that means is your f of 2.3, okay, is between 6.921 plus this number or 6.921 minus this number, your upper and lower bound. Does that make sense? Because if you're saying this is the most your error can be, and this is your approximation, then you either add it or subtract it, and that's your interval. So what that means, if we calculate it, is that this sits between, and I guess it's an equal here, so they're saying put equals here. So there's an equal here. Okay, so this sits between these two numbers, and you can put this in your calculator. 6.921, okay, plus this number, plus second answer, which would be 6.924 on this side, or if you subtract it. So I'll do 6.921 minus this number. Oh man, this calculator doesn't do it. Okay, forget it. Okay, that's because I bought this one on sale. Okay, 0.0030375. 6.917. Okay, so remember you can truncate or you can round correctly. Okay, guys, that truncating thing, I kind of feel like that's an AP thing. I feel like college professors would want you to round correctly. I would, but you can also truncate or round correctly on the AP test. All right, so right here, this is my number. So the question is, could this function be equal to 6.922? And all they're saying is 6.922 in this interval? So you say yes, because it lies on the interval. And then if they say, could this function be 6.927? You would say no, because it doesn't lie in the interval. You guys see how to answer the question. All right, so this is one example of a Lagrange problem, actually a pretty common example, where they just give you the maximum that derivative can be, okay? Here's another common, there's actually only 3 common ways that they do the Lagrange problem. So let me just tell you, the first common way is just the example we did, which was they just like throw the maximum derivative in your lap. Does that make sense? They just say, hey, it's 9, and you just plug it in, okay? This is what I call the cosine sine way, which we're about to do. And then the other way they could do it is they draw a graph. They'll draw a graph, and they'll say, hey, what derivative do you want? Do you want the 4th derivative? You know what? I'll graph the 4th derivative for you, okay? And then they'll draw a graph, and then they'll put some numbers on this graph. And so you have to be a little bit careful with this. And, you know, they might say 0 to 1, 2, 3, and such. And then here, let me just make this just all going up. Okay, but remember, it's the maximum derivative between the center and your C, you know, the center and your X. Okay, remember, our center was 2, and what was our X? 2.3. So then you come up here and you're like, okay, here's 2, here's 2.3. So like the biggest number of your derivative between 2 and 2.3. Does that make sense? Like sometimes you have to pull a maximum value off of your off of a graph. Okay, so just FYI, those are the 3 ways that we've seen AP ask for this Lagrange maximum derivative. And that's really it. That's all the ways we've seen them do it. Okay. All right, so let's look at this polynomial here. We want to write a polynomial of this function. Okay, do you see, I know the Maclaurin series for sine x, okay, but I'm moving from sine x to sine 5x plus pi over 3. What is that shift? What is that functional shift? Okay, left by pi over 3. Okay, what if I had the center? On the Maclaurin series, I know my center is 0. What's my new center here? 0. What's my shift there? 0 shift. Can I do substitution? No, because a function in the center did not shift together. So that's a bummer, okay? So what I'm going to do here is I'm actually going to do the table, because that's the only thing I know how to do if I can't just do substitution. All right, so I'm going to do the table here. So this is f of x. So I'm going to take the derivative of this. So the derivative of this is going to be cosine of 5x plus pi over 3 sine, the derivative of sine u is cosine u times the derivative of u, right? So times 5. And then I take the derivative of that. The derivative of cosine is negative sine of 5x plus pi over 3. But then I have to multiply by the derivative of the inside, which is 5. So do you see this turns to 25? Okay. Then I'm going to take the third derivative, and that's going to be, again, the derivative of sine is cosine. So that's the negative just carries down. This would be cosine of u times the derivative of my u, that's 5. So this will be 125. And I know I only need the third degree, but I'm going to go one more, guys, because I know I'm going to use Lagrange. So I'm going to use one more. And so this will be positive sine of 5x plus pi over 3. But I have to multiply the 125 by 5. So that's going to be 5 times 5 times 5 times 5, which is 625. Okay. On the right side, do you remember what you plug in? What do you plug in? Do you remember? Your center. Okay, so this is going to be 0, which is your center. So if you plug in 0 here, let me do it in a different color so I can get squished in a little bit more. If I plug in 0, I'll get sine of pi over 3. Okay, and that is square root of 3 over 2. Okay, if I plug in, oops, sorry, this is not a derivative. This is just f of 0. Okay, if I plug in f prime of 0, I'll get 5 of cosine of pi over 3. But that's 1/2. Cosine of pi over 3 is 1/2. So this is just 5 over 2. If I plug in 0 into the second derivative, I get negative 25 times sine of pi over 3. But remember, sine of pi over 3 is square root of 3 over 2. So this is negative 25 times the square root of 3 over 2. The third derivative will be negative 125 times the cosine of pi over 3. But remember, the cosine of pi over 3 is 1/2. So this is negative 125 over 2. And then finally, the fourth derivative, which they didn't ask me to do that, by the way, but I'm just doing it, okay, is equal to 625 times the sine of pi over 3, which is 625 square root of 3 over 2. Okay? All right, so I've calculated all of these things. And so what they asked me to do is put this into a Taylor series, okay? So the Taylor series is, what is this? This is sine of 5x plus pi over 3 is approximately equal to, I'm converting this function into like the sum of polynomials, okay? So this is equal to f of c, so that's square root of 3 over 2 plus, remember, 5/2. The center of this is 0, right? So it's x to the 1 over 1 factorial minus 25 square root of 3 over 2 x squared over 2 factorial minus 125 x third over 3 factorial. And I just need to go to the third degree, I think. And sometimes they call this p of x. It's fine. Okay. So then what they say next on this part here is they say use the Lagrange error bound. Okay. Use the Lagrange error bound to show me that the error, if I use these 4 terms, okay, show me that if I actually estimated in here, I would be wrong by no more than 1200. That's what they're saying. Do you understand that this right here is the error, right? They're saying that the error, show me that this error is less than 1200. All right, so if this is an alternating series, right, you just go to the next term. Is this an alternating series that converges? It has to be an alternating series that converges. Do you guys see it's not even an alternating series? Okay, so what that means is if I use this as the approximation, okay, but the approximation for what? What am I plugging x into? Am I doing something wrong, Ryan? Oh, where? Sorry. Oh, yeah, I did. Okay, so 2 right here. Okay, thank you. So if I say that this is approximation, plugging in x, and what are they telling me to plug in x here? Can you tell what the x is here? See, this is my p term, right? So they're saying plug in what for x? Okay, so make sure this is x equals 115. You actually have to be able to pull that out. What's my c in this problem? 0. Okay, so my center is 0 for this function, and my x is 115. So they're saying if you plugged in 115 here, so, you know, come in here and plug in 115. You actually don't have to. But if I plugged in everywhere there's an x, I put in 1 over you know, 1 over 15. Everywhere there's an x, I came in and put in 1 over 15, 1 over 15, 1 over 15. What's the most that I'll be wrong by? Okay, and that formula is kind of like the alternating series bound. But instead of putting the derivative here, it is a maximum derivative of now, was this third? This is third. This is the third derivative. So you go one more. So the next one would be the fourth derivative of z, okay, x minus c to the 4 over 4 factorial. Do you see where I'm getting this term? I'm just going to the next term, basically, okay? And this used to be, and I should say the max, sorry. So this is the max. This is the max. Okay, actually, let me rewrite this so that this can be neater. For Lagrange, this is the maximum of the next derivative. Okay, so this f to the fourth is not a fourth power, it's a derivative of the z, okay, absolute value, times x minus c raised to the 4 over 4 factorial. You just go to the next term, all right? So here's this, guys. What's my x in this problem? What's my c in this problem? Okay. What's my maximum derivative in this problem? Well, this is the fourth derivative, right? So what you do is, look, we found the fourth derivative down here. Here's the fourth derivative. Do you guys see it? This is why I knew to do the fourth derivative. So I did the fourth derivative, and all you have to do is come here, and what AP wants you to do, I know you could actually calculate. You could actually go in the calculator and graph this function and find the maximum value for this function. Okay, you could actually do that. But that's not what AP wants you to do. AP just wants you to say, hey, call this 1. The maximum that sine can be is 1, right? Because sine goes between -1 and 1. And we're doing the absolute value anyway. Okay, so that's 1. So the maximum this can be is 1. So this maximum is going to be 625. So what you're going to do is you're going to take 625 and put it in here. And then you're going to calculate that. Okay, so this is going to be 1 over 15 raised to the 4th power. So 1 divided by 15. I'm going to take that number. I'm going to raise it to the 4th power. Okay, I'm going to multiply it by 625. Okay, and I'm going to divide it by 4 factorial. So I'm going to divide it by 24. Okay, and this number here, this is my maximum error, 0.0005144. And there are more numbers here. This is the most my error can be, okay, using the Lagrange remainder theorem, if I plug in 1 over 15 for x, and I stop at the approximation of four terms, okay? Lagrange error bound. All right, so let me tell you, some of you guys are like, wait, I would never have known to put a 1 in here. Well, guys, there's only 3 things they do, okay? They do it over and over and over. The first one is they tell you what your max is. So that's just like this problem here. They said, hey, this is your max, just use the number. The second thing they do, they only do 3 things. The second thing they do is they give you a cosine sine problem, and then you just assume that if it were cosine, you'd still assume it's 1. Does that make sense? You assume that that part is 1, and you just get the absolute value of the number next to it, basically. Okay, that's the only thing they do. Or they give you a graph, and they say, choose the maximum number off this graph. Okay, all right. You guys are done.